Okay, great. Okay, welcome everybody. We're really happy to have you all here at the first plenary talk for the NCNGT 2021. It looks like people are participating and talking in the Discord, which is wonderful to see. We're really happy to have almost 400 participants this time. And I'm really excited to introduce our first plenary speaker, who is Jayadev Athreya. He is a professor of mathematics and the comparative history of ideas at the University of Washington. His work is in the geometry of surfaces and neighboring fields. And today he's going to be talking to us about a counting problem for certain graphs immersed in the flat torus. And I'm very excited about this talk, and I hope you all are as well. So the way we're going to do questions is that if you have a question, we're going to keep everybody muted. So please go ahead and make sure you're muted. And if you have a question, please message it to me directly. And if it's something that makes sense to ask in the middle of the talk, I will ask Jayadev that question. And if it's not, I'll let it go. And then at the end, there will be an opportunity for you to use the raise your hand function, which is under the reactions tab at the bottom of your screen. And that will show you asking a question during the question session and at the very end, and we'll unmute you and you can ask Jayadev your question directly. So I think that's everything. So let's get started. Go ahead, Jayadev.
Awesome. Thank you so much, first of all, for the opportunity. I want to say a special thanks to the organizers for putting together this really thoughtful and interesting meeting with this great format. I think it's easy to say, oh, we're going to have an online meeting and just throw some talks on Zoom. But the amount of thought you guys have put into this format is really, really lovely. And I think you guys are going to have a wonderful time. It's wonderful to see many old friends and new friends, hopefully in the Zoom. I also want to give a special thanks to Priyam for switching her talk with me on short notice and doing one of the hardest things in the world, rearranging skilled labor coming to your house to do important tasks. So Priyam, thank you very, very much, much appreciated. And I'm looking forward to watching the recording of your talk. I can't make it to your talk because I can't do the 17th, but I'm looking forward to watching the recording later. Okay, so let's go ahead and get started with today's talk. Hopefully will be at a level that's kind of elementary, because the result in some sense is I'm hoping this is the starting point of a story. I'm sharing with you guys something that I hope is the start of an interesting story. And at the end, I'm going to spend a bunch of time talking about potential directions it could go in, and nothing would make me happier than having some folks in this audience pick up on some of those directions and running with this. So the work I'm going to talk about today is joint with David Aulicino at Brooklyn College and Harry Richman at UW. There's no reason that Harry's name is smaller than David's. It's just that my handwriting is very erratic. Also, when I start doing some handwriting, if you can't read it, let me know. I will try and make it better. It was motivated with discussions with Andy Knightsky and Vincent Delacroix. I put their names down there because in some sense, this project wouldn't exist without discussions with them. And a lot of this was happening at MSRI in fall of 2019. So let's start with a really ill-posed problem. Maybe we have some big geodesic metric space. If you want, think about, let's say, R2 or the upper half plane with the hyperbolic metric, and you have maybe some finite collection of points hanging out. Each of you has picked points. So we have 69 points in the upper half plane or an R2. Now 70 as another person pops in. And then what's the most efficient way of connecting them? And of course, that's not a well-posed problem at all, because I haven't told you what I mean by efficient. Presumably it means some kind of vaguely distance minimizing, but you can think of there's some kind of action functional. If you want to make this a little bit more precise, maybe I want the points P to be maybe leaves of some kind of tree, perhaps. And this tree maybe to minimize some total length. And maybe then you can ask, are there going to be some internal vertices or so? But as Polya said, for every problem you can't solve, and especially for an ill-posed one, there's probably some simpler one that you can't solve. So here, let's start with one maybe concrete example of this kind of problem with this flavor, which is given 3 points in R2, say A, B, and C, find a point D such that the sum of the distances to D is minimized. So you have your given points A, B, and C, and then you want to minimize the sum of the distances to those points. And if you get bored during the talk, I urge you to try and work this problem out. It has a beautiful solution that we will come to probably at around the 15 or 20 minute mark of the talk. I definitely could not come up with a solution to this in 15 or 20 minutes, but I'm guessing there might be some people in here who might. So actually what we're going to be doing is we're going to be looking at such problems on surfaces, on compact surfaces, and we're going to have some kind of collection of points on the surface. Maybe I've drawn here a genus 3 surface with a flat metric with 4 singular points of angle pi. The graph paper indicates that it's a flat metric. No, I've just drawn a topological surface and I've marked these 4 points supposedly that have angle pi. And let's say I wanted to connect these points and I wanted to have a graph with these vertices as leads and internal vertices as trivalent and kind of equally spaced angles. And maybe I want this graph to be, I would like this graph to be isometrically immersed. So the edges of the graph to be geodesics. So these are called, some versions of these are called spectral networks or BPS webs. This is where Andy Knightsky's interest in the subject came in. These arise when you're studying maybe families of differentials and you're interested in counting these kind of combinatorial objects. And now I'm going to quote from The Simpsons, where I remember there was an episode where Lisa was asked a question and she said, the answer is yes, as long as you ask me no further follow-up question. So if you ask me what the physics connection to spectral networks and BPS webs, I will say, talk to Andy Knightsky. I know this, I could, he does a very good job and is very patient at explaining them to you, but I don't necessarily trust myself to pass that explanation on. But what I want to do, I like things on surfaces. I like counting things on surfaces. So I'm going to count such things. And Andy assures me that the physicists find some of these kinds of questions interesting. So here is the real start of the talk. That was kind of all throat clearing. So what we're going to do is we're going to restrict, I gave you this very ambitious picture of this genus 3 surface with 4 singular points, but really at this point, we don't know how to answer questions on those kinds of surfaces. Let's start with the simplest possible compact flat surface. Okay, so I said compact, so let's do the torus, right? To my mind, that's the simplest possible compact flat surface. No singular points, great. And let's just be very concrete. And let's just take the square torus for right now. Okay, so we're going to take the square torus. Everything I'm going to say is going to work for other tori as well, but just to make everything easy, I'm going to do it the square torus. And what we're going to do is we're going to try and count tripods. So what we're going to do is we're going to mark the point 0. So that's marked in blue, on that kind of electric blue. The torus is there. It has those red sides and blue sides, which are identified. And a tripod consists of a non-zero point in the torus. And then I shoot out straight line segments equally spaced at angles 2 pi over 3. And then all of those trajectories end at 0. Okay, so you see an example right here in this small picture, right? So you see this, that's one example of a tripod. All of those angles are 2 pi over 3. All the things end at 0. And this one, of course, is even embedded. So another way of saying this is you take a metric graph sitting inside of the complex plane. Let's say you have 0 going to L1 along the horizontal axis, L2 along the line e to the 2 pi I over 3, and L3 along the line e to the 4 pi I over 3. And then you map all the endpoints, L1, L2 e to the 2 pi over 3, L3 e to the 4 pi over 3. You map all of those to 0. And slightly confusingly, you map 0 to this tripod point P. And here I'm saying I want an isometric immersion with respect to the inherited metric from C on the graph G and the natural flat metric on the flat torus. And then we denote the pair GI, the graph together with the immersion, by tripod. And we say the length of the tripod is just the sum of the lengths. Notice, let's compare this. Suppose instead of shooting out 3 segments from my point, I just shot out 2 angularly equally spaced segments. Those would then be at angle pi, and I would be asking for a closed geodesic through 0. Right? So this is a very natural generalization of a closed geodesic passing through 0. It's also, right, it's a natural generalization of closed geodesic passing through zero, which says start at a point, shoot out things at angle pi, and both hit zero. And this is an isometric immersion of this graph, the graph with one vertex and one edge. That's a closed geodesic. And what we're really looking at is kind of equiangular immersions of this. This is, and thank you to Francis Bonahan for suggesting this interpretation of what we call a theta graph. So, right, it's called a theta graph, not because it has anything to do with theta other than it looks like the Greek letter theta, right? So you have this graph that looks like the Greek letter theta. You shoot out things at equal, you think of each vertex as having equal angles. And then it's also, there's a little exercise hiding in here, which is if you have this tripod, if you go back, for instance, if you see how all the things are meeting at the zero, they're also meeting at angles 2 pi over 3 there. It's a fun little thing to check. Not particularly hard. So, okay, questions about what a tripod is at this point. Okay. Awesome. So many different ways of thinking about it. I like this. The theta graph interpretation is kind of nice. And the question we're going to try and understand is we're just going to count them, right? So we're going to try and understand the R goes to infinity asymptotics of number of what we call primitive tripods, a primitive tripod of length less than or equal to R, a number of primitive tripods of length less than or equal to R. And what we're going to do is we're going to sketch a proof of the following, that the number of primitive tripods this is the theorem of Harry, David, and I. By the way, there's some construction going on outside my window. Can you guys hear it? Should I close my window? Is everything okay? Excellent. So the answer is that it's 1 over zeta of 4 square root of 3 pi over 24 times r to the power 4. And the reason I'm being very specific about these numbers is, one, I find these numbers pretty. Two, I hope that these numbers are going to be ratios of volumes of certain moduli spaces. I don't know that yet, but I hope, and maybe I can actually say I expect that these numbers will be ratios of certain volumes of moduli spaces. But I still, that's one of the things where we're at the very start of a story. Okay, so it's 15 square root of 3 over 4 pi cubed. Notice this is in kind of Q adjoined square. It's in a very small algebraic number field together with pi, right? That's basically where we are. Here, this asymptotics means the ratio goes to 1 as r goes to infinity. What we're going to do is we're going to prove this claim by turning our problem into a problem about counting pairs of Gaussian integers satisfying certain conditions. And our definition of primitivity, by the way, is it's primitive if you're not a scaled copy of another tripod. What that basically means is if your z here, if your z is kind of m plus ni and your w is this s plus ti are your Gaussian integers, then the associated, what it's going to become is that the associated 4 tuple of integers actually has GCD 1. And the proportion of primitive integer points in all integer points is 1 in dimension n is 1 over zeta of n. That's I'll say a little bit more about that in a second. The square root of 3 pi over 24 is going to be the volume of a certain region in r to the 4. So that's in blue. And then the r to the power 4 itself is just a dimensional count. It's saying we're counting things. We're counting integer points in 4 real dimensions, and so that's why you're getting an r to the power 4. So that's what the explanation for all of these numbers is. So again, going back to this idea of counting primitive closed geodesics on the flat torus, if you count primitive closed geodesics passing through the origin, passing through 0, that has this asymptotics 1 over zeta of 2 pi r squared. And I realized I didn't use my colors as well as I should have. They're slightly different than they were on the last page. This 1 over zeta of 2 is the probability that a randomly chosen integer vector in a large ball is primitive. It's the proportion of primitive vectors over all vectors. And that's just because here's the heuristic for that. If you have m and n, what's an obstruction to them being primitive? It's them being divisible by the same prime, p. The probability that they're both divisible by a prime p is 1 over p squared, right? They both have to be congruent to 0 mod p. There's p equivalence classes mod p. So the probability that they are both not, that they are that they are both divisible by p is 1 over p squared. So you take 1 minus 1 over p squared, and you take the product of that, and then that's 1 over zeta of 2. And then in n dimensions, it's 1 minus 1 over p to the power 4. Right? And there's, of course, this is a heuristic because it's not really independent and so on, but it's a pretty good heuristic. This pi is the volume of the ball of radius 1. And then r squared, that's r to the power 2. We're counting integer points in the dilates of a ball, and we're counting primitive ones. And similarly here, we're going to be counting integer points in the dilates of some region, and we're going to be counting primitive ones. So that's how this is almost exactly the same set of ideas as this thing here. Okay. So now let's get back to our tripods. Quick little LaTeX note. If you want to write a paper about tripods, the command down capital Y gives you that little tripod symbol. I was very happy when I found that out. So note that if we lift a primitive tripod we can lift it from the torus to the universal cover, right? Let's lift it to C. And now we're going to obtain some center point. Of course, the center point is not well defined. It's only defined up to translation, but we pick one of the lifts, p tilde, and we have segments emanating from p tilde to points in the Gaussian integers, right? They're hitting 0, so they have to have points in the Gaussian integers. And what we're going to do is we're going to take one of those points to be 0, right? We can always do that. And we're going to call the other z and w. And we're going to remove some of the ambiguity from the situation by insisting that the largest angle of this triangle, 0zw, is at 0. That means it's opposite the largest side. So we mean that, so in terms of just w and z, absolute value of w minus z is bigger than or equal to absolute value of z and absolute value of w. And now here is something pretty. Now we're going to get to the answer to that question that I posed at the very start of the talk about, so how do we compute the length of this tripod of zw? And again, only certain pairs are actually going to yield a tripod. But I'm going to tell you how we can compute this length in terms of z and w. Here's this beautiful, beautiful, beautiful result. It's called the Fermat point. I imagine people have thought about this for some time. A Euclidean triangle has an inscribed tripod if and only if all of the angles are less than 2 pi over 3. That is, the largest angle is less than 2 pi over 3. In this case, the center of the tripod can be constructed as follows. On each side of your original triangle, so you build a equilateral triangle. So here, my original triangle has 3 colors. It has the colors sort of pink, blue, and kind of brown. And then on top of each of those sides, I've built an equilateral triangle in the same color, right? And then you connect the opposite vertex to the opposite vertex, right? The opposite vertex of the equilateral triangle to the opposite vertex to the side you're on. All those 3 lines turn out to intersect in one point. That one point is the tripod point. And if you connect those, if you highlighted it in kind of electric green here, that's the tripod. Moreover, the length of the tripod, the total length of the tripod, is the length of any one of those lines. All of those lines have the same length, and that's the total length of the tripod. I think that's really cool. I think that's an exercise you could give technically, you could probably give it to a high school Euclidean geometry class, and they could do it, I'm sure, with some effort. And I think that's really beautiful. So the length of the tripod is the length of any one of those lines. Again, if you get bored, lots of fun to just sit down and prove this by drawing some circles and stuff. I feel like this should be some sort of bonus level in Euclid the game. Okay. So the claim is the length of, so now using this, we can write the length of the tripod as w plus z minus w e to the I pi over 3, or z minus w e to the I pi over 3, w minus z e to the minus I pi over 3. I shaded in corresponding colors the lengths of each of those segments, right? And the claim is all of those lengths are actually the same, and that's the length of the tripod itself. And the length of the tripod, of course, is the length of, it's the absolute value of the point. So if you can see my labels here, right? You have the point P, the points w plus z minus w to the I pi over 3, z to the I minus I pi over 3, w. But the length of the tripod is absolute value of p, absolute value of z minus p, absolute value of w minus p, all added together. But then the point is the angles at p are all 2 pi over 3. So by rotating appropriately, you can make all of them parallel. And so you can make some of their absolute values actually equal to the absolute value. You can just add them up, right? And you can just take the absolute values adding up. And now you can bring the addition inside the absolute values. And then just a little bit of algebra gets you to this electric blue line. So you get the length of the tripod is the length of the electric blue line. And then it's not very hard to do a little bit of algebra with e to the I pi over 3 or e to the 2 pi I over 3 to get that it's equal to the pink and the brown, right? You're basically using these facts that e to the I pi over 3 is plus e to the minus I pi over 3 is 1, and for 2 pi over 3, the corresponding thing is negative. The real part, basically the real parts are a half and negative a half. Okay. Questions about this computation of length is again based on this Euclidean geometry fact. Okay. So in particular, how does this connect to the original thing that I posed about this efficiency? It turns out that this point P minimizes the function f of zeta is absolute value of zeta plus z minus zeta plus w minus zeta. And this is called the Fermat point of the triangle. So this tree is kind of the most efficient way of connecting the points 0, z, and w, right? So it's going back to that thing. And this resulting tripod is something called the Steiner tree. And there's a whole literature in kind of combinatorial geometry and optimization on these things called Steiner trees. So that's one direction you could go in, is you could say, well, what happens if I took sort of 4 points and started looking at this question, or 5 points and so on, and what kind of graphs would I get? And there's a lot of literature. Steiner trees, people care about these things in various graphs. For this audience, I think you could start to look at Steiner trees and think, say, what do Steiner trees look like in various, I don't know, Cayley graphs of interesting groups? I think there's lots and lots of interesting things from this family of questions about Steiner trees. So we'll come back to that if we have some time at the end of the talk. I also want to mention that we could consider different notions of tripod length. What we've looked at is a kind of L1 notion, right? We just added up the lengths. You could look at a kind of L2 notion, which is square the lengths, add them up, and take the square root. You could also look at a kind of triangular notion, which is look at the inscribed triangle and take the perimeter of that. Or you could look at an L2 triangular notion. You could square all you could take a kind of view the sides of the triangle as a vector and take the L2 norm of that. And all of these lengths have nice relations. The law of cosines tells you that these various lengths have, because the internal angles of the tripod are 2 pi over 3, gives you this beautiful formula that says that L1 squared, capital L1 squared is little l2 squared plus little l3 squared plus L2 L3. Really looks like these nice kind of symmetric, homogeneous polynomial symmetric functions. I feel like there's some kinds of potentially interesting algebra connections there. I haven't really explored that. But here's a nice identity. The L2 triangle length squared times 2 is 3 times the L2 length squared plus the L1 length squared. And that's just a fun identity that pops right out from this. And I should just mention that the counting we could do it for these other countings as well, counting graded by these other notions of length. Just the constants in front would be different because the volumes that we're computing would be different. And we haven't yet computed those volumes, but that's, I think, an interesting project and might be a nice even project if you're looking for a student, or if you are a student, might be a nice project to do. Okay, back to our counting problem. So let's lift our tripod from C to the, we've lifted our tripod, we've made the largest angle at 0. So we have to have it opposite the largest side. So Z minus W is bigger than or equal to ZW. And then we need the largest angle to be less than 2 pi over 3 to actually have a tripod, right? That's what we said earlier. So for that, again, using the law of cosines, bet you didn't think you'd hear the law of cosines this many times in this geometry topology seminar talk. Z minus W squared, Z squared plus W squared minus 2ZW cosine theta, cosine's decreasing on 0 pi. I just also finished creating my geometry class. So I'm very, one of the problems was to compute the area of a certain hyperbolic triangle in the upper half plane. So I'm very familiar with the fact that cosine's decreasing on 0 pi. So theta is less than or equal to 2 pi over 3 means that cosine is bigger than or equal to negative a half. So you can rewrite this condition purely in terms of these lengths. So it's just that Z squared plus W squared, Z plus W quantity squared is bigger than Z minus W squared plus ZW. And then the length of the tripod is what we computed earlier, Z e to the I pi over 3 plus W e to the minus I pi over 3, which is less than or equal to R. Okay. So here's what our counting problem is now. Count Z equals X plus IY, W equals U plus IV, GCD is XY, GCD of XY UV is 1. That's the primitivity condition. Then we have this angle condition. So B summarizes both the largest angle being at 0 and that angle being less than 2 pi over 3. Notice that that's scale invariant. If I were to scale Z and W by the same thing, right, this if I scale Z and W by some factor T, this inequality stays the same, right? It's homogeneous. And finally, I have this length inequality, Z e to the I pi over 3 plus W e to the minus I pi over 3. Now, this is a lattice point counting problem, I claim, in the dilates of a fixed region. This is just if I just took the region where I replaced R by 1, this is just the scaling of that region by R, right? Because the middle thing B doesn't change with scaling, and the bottom thing C does, but it changes linearly with this scaling. So here's a standard result in lattice point counting, which is if you have a nice enough region and you want to count lattice points in it, nice enough maybe means, say, smooth. I mean, smooth boundary is certainly way more than nice enough. Smooth boundary, and you want to count lattice points in the dilate, then the number of lattice points is proportional to the volume. And then if you count primitive lattice points, you just put a 1 over zeta in front. And that goes back to, for instance, you can find it written down even in Hardy and Wright number theory books. So it goes back at least 70 or 80 or maybe 100 years, if not further. So our problem now is, so in some sense, if you just said, oh, I want to know that there is some asymptotics, we're kind of done, right? It's 1 over zeta for R to the 4 times the volume of this region. But I'm actually, so just like in the closed geodesic case, 6 over pi squared, or pi squared over 6, is a really interesting number. It's 6 over pi squared is 1 over the volume of the moduli space of abelian differentials on flat tori. It's the pi squared over 6 is the volume of the moduli space of once punctured tori. I have this suspicion that this counting problem is also related to volumes of certain moduli spaces. If I had to guess, it would be volumes of cubic differentials, spaces of cubic differentials. I'm speculating now. But in particular, I just want to make the case that computing this volume exactly is interesting. And so I want to tell you a little bit. Also, this was my first kind of pandemic project. I started doing this computation in like March, and it really kind of kept me sane through the first couple of months of the pandemic. Now, I should also say that you're not going to find this computation in our eventual preprint because Harry found a much slicker and prettier way of doing it. But damn it, I went through 2 months of pain, so I'm going to share it with you. Okay. Harry found a way of transforming this region using a nice linear change of coordinates to one where you could really compute the volume very easily. And then all you have to do is compute the determinant of this linear change of coordinates. So I'll just say that Harry's way is much better. But I want to share with you this way because it's kind of cool, I think. And it has more geometry in it. Okay, so what we're going to do is we're going to call this region omega tripod. The region in yellow, which is the zeta omega in C2, satisfying conditions 1 and 2. And now what we're going to do is we're going to fix the first coordinate zeta, and then we're going to consider the set of omega and the fiber over it. So that's the set of omega satisfying the conditions just with a fixed zeta. And it's not so hard to convince yourself that this volume only depends on the magnitude of zeta. Everything, as you can see, everything in here kind of has a magnitude of zeta. If you were to move zeta by some e to the I theta, you would just move omega by the same e to the I theta. So you would just be applying a rotation with the set of to the fiber as well. Right? So I write that here. Omega tripod sub zeta e to the I theta is just e to the I theta omega tripod of zeta. And so what we're going to do is we're only going to consider real parameters for the base. So what we're going to do is we're going to compute the volumes of these fibers. Those are just areas. And then we're going to integrate those over the possible base values, right? And then we'll be done. So we put zeta is equal to S positive. And then the condition that zeta minus omega is bigger than or equal to zeta, that means that S minus omega is bigger than or equal to S. That means omega is outside the ball of radius S centered at S. So it's outside of this electric green circle. We also want omega in the region between the positive x-axis and t e to the 2 pi over 3, right? We want the angle between omega and zeta. Zeta is on the Zeta is s now. It's on the x-axis. So we want that angle to be less than 2 pi over 3. So we want to be in this region between the electric blue ray and this, I don't know, magenta, fuchsia ray. And then zeta minus omega is bigger than or equal to omega, right? We need that too. We need it to be the longest. If you write omega as x plus iy, a little bit of computation gets that you need the x coordinate to be less than or equal to s plus, less than s over 2. So you need to be the left of this yellow line. And then finally, this length condition that zeta e to the I pi over 3 plus omega e to the minus I pi over 3 being less than 1, a little bit of algebra rewrites it to omega minus s e to the I minus I pi over 3 less than or equal to 1. So you have to be in the ball of radius 1, inside the ball of radius 1 around this other point, which happens to be on the same vertical line that we cared about earlier. So after all that work, I drew a region. In this case, the region is actually empty because I got to be outside the green circle, in between the blue and the fuchsia lines, to the left of the yellow one, and inside the brown circle. There's nothing here. There's nothing in this particular case. So what was the issue is, that was a case where I drew a picture where s was actually bigger than 1. And then there's actually nothing in there. The region actually changes shape at s equals 1 over root 3 when the circles all and the line all intersect at a particular point, 1 over root 3, e to the I pi over 3. You can see the computation there. A crucial point for us, though, is that the line t to the I 2 pi over 3 is actually going to pass through our point where our circle is centered, s e to the minus I pi over 3. So here's some actual pictures with the region actually being non-trivial. I don't know why I specified hand-drawn, as if anyone would thought that I generated this picture with a computer program. But here's a hand-drawn picture. This is s equals a half. It's actually not a bad picture, if I say so myself. The circles don't look particularly like circles, but this is what the region looks like there. You can see the brown circle is actually quite big. Here's a better picture using Desmos. This is the picture for s equals 0.34. It's less than 1 over root 3. You can see it's got 2 circle arc boundaries and 2 straight line boundaries. And just as a little bit of foreshadowing, what we're going to do eventually is we're going to treat this point as our origin. And then this region is really nice. It's in between 2 lines through the origin. And then a circle arc centered at the origin, and then another circle arc, which is not centered at the origin, but passes through the origin at least. Yeah. Okay. Here's some pictures of the region. This is s bigger than 1 over 3. It becomes this kind of triangular region. And it kind of disappears as you get closer and closer to 1. When s becomes 1, the region just becomes a point. It degenerates. So let's look at v of s to be the volume of the region omega tripod s. Then the volume of the region omega tripod is the integral of s v of s, 0 to 1, and then theta goes from 0 to 2 pi. So just 2 pi integral 0 to 1 s v of s, right? You got to have that s in there, polar coordinates. And then I claim that v of s is actually equal to the integral, equal to these integrals because of how I've set it up. The key idea is we're going to use polar coordinates for this region based at s e to the minus I pi over 3, with theta equals 0 being the line passing through the point s. And then b of ss is this. Real part of omega equals s over 2 is theta equals pi over 6. And argument of omega equals 2 pi over 3 is line theta equals pi over 3. Okay. So this becomes, so I made a slightly inaccurate picture here. My 0 angle is this, and then this is pi over 6. This becomes pi over 3. This becomes r equals 1. And you'll see another picture of this in a minute. So all of these things become really nice in polar coordinates based at this point. What you end up getting, again, here is the picture now. That's theta equals 0. Theta equals pi over 6. Theta equals arc sine of 1 over 2s. R equals 2s cosine theta. R equals 1. In this case, your v of s is actually the integral because your theta goes from arc sine of 1 over 2s, arc cosine of 1 over 2s. And here's a picture where it's quadrilateral, and you're actually getting all the way from pi over s to pi over 3. So we see that, so basically, just to summarize, our region is omega S tripod is S e to the minus I pi over 3 plus R e to the I theta, where R is in between 2S cosine theta and 1, and theta is in between the max of arc cosine of 1 over 2S and pi over 6 and pi over 3. Very nice region. Now it's a calculus exercise, right? To compute this volume. So the volume is this, what I wrote down is this integral 1/2, 1 minus 4S squared cos squared theta d theta on this region. So for S0 equals 1 over root 3, that's where this cosine, arc cosine of 1 over 2S is actually equal to pi over 6. So the max is achieved, they're equal there. So now you compute these integrals, and you compute the integral where they're on the one region, it's very easy, right? When you just have from pi over 6 to pi over 3, you just get this polynomial. When it's arc cosine 1 over 2S, you get the slightly more complicated integral. Again, not terrible, right? So this is just the computation. You have to work a little bit, but that's what you get. But now we have to do another integral. We have to, so this is what V of S is, right? So we've computed what V of S is in both these regions. I'm not going through the details. I trust that we can all kind of take, with enough time, go through this calculus. But now we want to compute SV of S, integral of SV of S. And now what we're going to do is we're going to break it up into two pieces. We're going to break it up into the easy piece from 0 to pi over 0 to 1 over root 3, where the function V of S is really just a polynomial in S, and you get this pi over 108 from that, easy to compute. But now we have the second integral from 1 over root 3 to 1 of this thing that has all of these arc coses in it, and it has like polynomials time arc coses in it. So now what we're going to do is we're going to break this up into various pieces. And remember, there's also this S sitting on the outside. So we're going to break it up into pieces that are easy. The pieces 1, 3, and 4 are easy, and the piece 2 is hard. So 1 gives you a pi over 18. 3 gives you a 2 pi over 27, root 3 over 18 with a negative sign in front. Again, just a polynomial. 4, you have to be a little clever. You have to use a u sub, 1 u sub, and then you get this 13 over 72 root 3. So we have some pi's, we have some root 3s. And remember, we also have this pi sitting out front in the end from our computation, right? Because we have this, eventually it's going to be 2 pi integral of SV of S. And then the integral 2, I pounded away at it for a while, and then I just gave up and plugged it into Wolfram Alpha, and it said, oh, here's what it is. And it turns out it does actually have a nice indefinite integral. I did verify, I did differentiate that and get the answer, so it is true. And you get this 1 over 2, 1 over 216, 7 root 3 plus 4 pi. And now what's cool is you add all these pieces up. This is SV of S ds is A plus 1 plus 2 plus 3 plus 4. And you get these terms with pi in them, and you get these terms with root 3 in them. And all the terms with pi in them disappear. They cancel. So you only get one factor of pi sitting out front from the volume because it's this 2 pi sitting in front. All the other pi's disappear. It's not a mixed pi in root 3. It is, but there's no like 2 additive terms. It's just one single term, which it makes you believe that there's something cool and interesting going on. So you get this root 3 over 48, and then you get the volume is 2 pi times that root 3 over 48. It's root 3 over 24. And then if you multiply, if you want this primitive thing, you get 1 over zeta of 4. And then that's 90 over pi to the 4. And so you get this 15 root 3 over 4 pi cubed. Again, to reiterate, the lattice point counting problem comes from the fact that omega tripod R is R omega tripod. And in general, for nice regions, the number of primitive points in the region is the volume of the region times R to the 4 divided by zeta of 4. Now, I want to now it's the last 3 minutes of the talk, so I want to speculate some more. There is beautiful recent work of Koziars and Nguyen who talk about counting certain equilateral triangulations of flat surfaces and getting asymptotics that look like pi to some function of genus Q adjoint square, whose leading term looks like pi f of g q times q adjoint square root of 3, something q adjoint square root of 3. We have not yet been able to put our results in their framework in a way that makes the numerology of their genus match up, but there's got to be a connection. I mean, it just feels like there has to be. I will say that actually what we're kind of doing, and I want to share with you this picture. This is a picture of the tripod associated to the integer points, the Gaussian integers 4 plus I and 3I. I wanted to make this the picture because I wanted to be clear that the integers themselves don't need to be primitive. The Gaussian integers here, omega is not primitive, or W is not primitive, but Z is, and Z together with W is primitive. This is a tripod that sits inside, and then if you look at the determinant of the sort of 4, 1, 1, 3, that's 11. And if you count the number of transverse self-intersections, that's 11. It's not a coincidence. It turns out that that's actually the general case, because what we're actually doing in some sense, anytime you have a tripod, you have a picture like this, right? And then you could look at the lattice generated by Z and W. That's a sublattice of the Gaussian integers. That's a cover of your torus. What you're actually doing is we're counting equiangular hexagonal decompositions of covers of our torus. This picture, if you look at a big fundamental domain for the torus generated by Z and W, which is kind of doubles this triangle, the red, green, and blue lines on that torus give you a way of expressing that torus as a hexagon with opposite sides identified. And the vertices of the hexagon are your tripod point and are the point ZW, the 0 point for your torus. So what we're doing is we're counting, equiangular hexagonal decompositions of covers of tori. That's another framing of our counting problem, which I think is kind of cool. I also had a massive brain freeze at some point where I was like, equiangular? That means the hexagons are regular. And I was like, does this mean that all of these things have regular hexagonal decompositions? Yes, with some base point fixed. I'm marking a 0. Yes, absolutely. Marked points, exactly. But of course, I then remembered the word rectangle and remember that equiangular polygons don't have to be regular except in the triangle setting. Yeah, so I'll just share very briefly. These are some emails from Andy Knightsky. I'm just flashing these up just to show the fancy part about how what we're hoping for is that these are related to what we're eventually hoping for is that these will be related to representations of the fundamental group of a surface into SLN and lists of differentials associated to this. We're hoping also that this will have some relationship to recent work of Vladimir Falk and Alexander Thomas about what are called higher complex structures. I see that Aaron is here, Aaron Fenyas. He's a good person to ask about some of these things, and maybe he's someone I should talk to about potential connections here. What are some other generalizations or things that we'd like to do? Obviously, I'm a translation surface person. Count these things on translation surfaces. Here are 3 tripods on a L, just lifts of the ones from the torus. More generally, you could look for other L's or other translation surfaces and count tripods where you maybe want the leaves to all be at singular points. You could do it on a hyperbolic surface. Why not do it on a hyperbolic surface? Fix a couple of points and ask for equiangular graphs, 2 pi over 3 at each vertex, and these kinds of connections. Can we count those? It's a natural generalization of a closed geodesic. Take your favorite point, shoot out three things, and ask them all to end at some fixed particular point. Can we count those? And that would certainly require a different set of ideas than what I outlined here. But so I think there's lots and lots of things that you can go with this. And I'm hoping that this was kind of fun and you guys will pick this up and run with it. So I think that's a good place for me to stop. So thank you for your attention.
Great. Thanks so much, Jayadev. Let's all thank our speaker.